name is Chien-Chun, and I come from the University Institute of Fabrication Mechanics. And let me start my presentation. And this is my outline. And now we will talk about introduction and the design and fabrication and the experiment results and the conclusions. And first, I will talk about the tactile sensor is a very important device. It's used in robotic control and human-machine interface and healthcare. And this is quite art. And the tactile sensors has been developed have different mechanisms, such like the piezoelectrode or resistance or capacitance or any other techniques. And the advantage of capacitance tactile sensors is good flexible and higher sensitivity, higher linearity, simply packaging, and easy expanding. And this is a tactile sensors, and the tactile sensors capacitance change of the gap air is changed if the force is applied. So in this tech, we have a concept that we want to utilize the ornate epidermal cell structure to replace the traditional capacitive tactile sensor, and that is the concept. And this is the ornate epidermal cells. This is the ornate epidermal cells, and this is the ornate epidermal cells in the SEM. And now we can see the structure. The width is about 50 micron, and the height is about 30 micron, and the length is about 100 to 200 micron. And we want to use this structure. And this is the fabrication. Now, a single ornate epidermal cells we pleat off and dry, and now we coating a pairing on top and the bottom layer to protect the electric short. And finally, when we coating a gold, we coating a gold to be electron, and the gold and the electron width is about 3 millimeters. And so each onion tactile sensors area is about 3 cross 3 millimeter square. And this figure is show the onion tactile sensor array. This is the onion tactile sensors microstructure. Now we can see there is a microstructure. The onion cell wall is about 1 micron. Pairing is 1 micron, and the gold is 24 nanometers. And we assume the convertible circuit. Now every single cell's side wall, we can measure it just like a spring, and with a spring constant K. And the gap of a button and a button cell wall, and we can measure that by a variable impedance Z, and a layer of onion impedance cells, and we can measure that by a constant K, and a variable impedance is a parallel contact together. And finally, in here, the variable impedance Z. And in here, the variable impedance Z, we can measure it just an onion resistance and an onion capacitance and a parasitic introduction is in series. Then, and we use the impedance analysis to define the value of RCL, and the result of the value is resistance is about a min ohm, and the capacitance is about 47 picofarad, and the parasitic introduction is about 120 nanohenry. And this is an equivalent equation And the total force and the total capacitance is shown in this equation. And the epsilon is only a dielectric constant. And when the force is applied, the gap will be changed, and so the total capacitance will be changed. And this is my experiment setup. And the low field is to measurement the force, and the maximum resolution is 0.01 Newton, and force range is 0 to 5 Newton. And the state control is to manifest about distance, and the highest resolution is 15 nanometer. And the accelerometer is a mixture capacitance. The range is 1 volt at 2 megahertz. This is the result. And this is the result about capacitance pressure response, and the force and the displacement response. And it's showing this figure, okay? And the measure the initial capacitance of the onion tactile sensors is 9 picofarad. And the maximum slope of relativity capacitance change of the onion tactile sensor within 1 kilopart, and range is 0.14 over kilopart. Each point is an average of 5 times measurement. The slope of force displacement response within 0.1 Newton. Range is 7700 Newton over meter. And this is a result of immediation response and the dynamic response. The immediate response is the applied force is increased 0 to the maximum force 5 Newton, and decreased to 0. And the dynamic response and cycle of loading and unloading tests. And in here, the weather is 10 gram, and pressure is about 1 kilopart, and time is about 10 seconds. It's the same of the process as continually repeats 5 times. And this is the pressure distribution of the onion tactile sensors. And the dark red is in the pressure control. It's a highly pressured and highly capacitance. The pressure controls are consistent with applied pressure is obtained. Okay, the pressure controls are smoothed by the data and the interpretation in the subweight origin A. And this is a technology comparison of this study. And this process is different. We use the Botanical Epidermal cell space. And the sensing mechanism is the same as the capacitance. And the sensor dimension is 3 cross 3 millimeter square. And the maximum applied force is about 2 Newton. And the sensitivity is 0.14 over kilopart. Conclusion: the maximum slope of relativity capacitance change of the onion tactile sensor within the 1 kilopart range is 0.14 over kilopart. And the single layer of onion epidermal cells is relevant for the high tactile sensitivity, and the mechanical flexible and optical transmission of potentially low-cost sensors and manufacturing in large area. And the onion epidermal cells can effectively reduce the complexity of the sensor structure, and those simplify the device fabrication process. Utilize the fabricate broadcast flow sensor array. Tactile imagery crossed by the acrylic stamp of a different shape will specifically demonstrate